One essential topic that you'll really need for understanding cellular energetics and the role of oxygen is redox reactions. So if you know what these are and you're comfortable with the terminology like reduction, oxidation, electron acceptor, electron donor, you can skip this video. But if you're not sure what these are, this is a very good place to start. So let's keep going. Okay, what is a chemical reaction? Well, in a chemical reaction, two or more molecules interact in a way that changes them into different molecules. So we're going to keep looking at this example. A plus B becomes C plus D. And one thing to note about this is each molecule is made up of atoms, and what happens in a chemical reaction is they trade some of those atoms. And so in this reaction, most of the atoms of A end up in molecule C, and most of the atoms of B end up in molecule D. That will be a useful thing to remember as we continue. So these are the molecules that make up, or the atoms that make up most of the molecules in cells. And atoms are made of protons, neutrons, and electrons, and we are mostly going to be paying attention to electrons because that's what forms the bonds that hold atoms together. So chemistry often just examines what happens to electrons. This isn't a new thing I'm going to test you on. This is supposed to be review. So chemical reactions change the bonds between atoms. That's really all they do, and that's a good way to think about them. So let's think in a little more detail. So A and B are going to react and become B and C. What's going to happen? Well, A and B are going to break some of their bonds, and they're going to trade atoms, and they'll form new bonds. And all of this involves electrons, and this is really how to describe any chemical reaction that we would ever pay attention to. So in redox reactions, there's an extra part, a very big extra part that we haven't seen in the reactions we've looked at so far. Redox reactions have all of the same attributes that I've just described. So the reaction leads to a trading of atoms and breaking and forming of new bonds, but also in a redox reaction, one of the molecules donates electrons to the other. So it doesn't just form new bonds, it actually donates the electrons. And that's an essential part of any redox reaction. It can't happen without that donation of electrons happening. Now, redox reactions are Now, since one of them donates to the other, donates electrons, that gives us the terminology of electron donors and electron acceptors. And that's the terminology I'm going to use in this course. So if you're used to hearing reductions and oxidations, we're not going to go there. We're going to talk about electron donors and electron acceptors. So again, this is our reaction, but this could be a redox reaction and we couldn't tell from the way it's written. So in a redox reaction, electrons would go from B to A, but we can't see that. So what we can do with redox reaction is rewrite this as two half reactions. And these half reactions will involve electrons. Electrons are abbreviated E minus. So one of these half reactions, if B is donating to A, B becomes D. So remember, most of the atoms of B become D, most of the atoms of A become C. B becomes D plus 2 electrons. So as it goes through this reaction, B loses 2 electrons and becomes D. Likewise, A, this is going to gain the electrons, and so if you combine A and those 2 electrons, A will become C. So A has to gain those electrons before it can go through its part of the reaction. So A is the electron acceptor, B is electron donor. And you can see this in the way the half reactions are written. B donates the electrons because it starts with them and it ends as something else and two free electrons that are not part of a molecule. And then A is the electron acceptor, you can tell because it starts by itself with free electrons and ends up as a combination of itself and of those electrons. So it has gained them. And so this is very important and useful. So if you look up redox reaction anywhere, you're going to see these sorts of things. So what this gives us is electrical energy. This is what electrical energy is often based on, especially with things like batteries or cell batteries. They are based on redox chemistry, where somehow chemistry is used to push electrons onto a wire, and the electrons flow through the wire to another place. And that flow gives us electrical current, which is a form of energy that can be used to light up light bulbs or phones or cars or whatever. So we can look through this example and think of it in terms of redox. Nothing happens with this battery unless we connect something to both terminals, unless there's some kind of a circuit connecting them. And that's because electrons have to leave this end and electrons have to come to this end. That has to happen for this battery to do anything. And there are two half reactions happening in this battery. So there's one set of half reactions here that donates the electrons, and they have to lose those electrons in order for that reaction to happen. And then over here, there are reactions that gain the electrons, and they must gain the electrons in order for those reactions to happen. So A to C, the accepting reaction happens at the positive terminal, and B going to C happens at the negative terminal, and together they make an overall reaction. A plus B becomes C plus D, and that involves electrical current flowing. So this is where we are most likely to see redox chemistry in our daily life. And so batteries are good examples of this, but cells are also good examples of this. In a very big way, every cell in your body can do this. But instead of little wires, we have molecules that carry the electrons around. And instead of a battery with two half reactions, you have half reactions involving electron donors, such as glucose, and half reactions involving electron acceptors, such as oxygen. So something we are going to see is those different types of molecules, and some of them are good at accepting electrons. Oxygen is a very good electron acceptor. That's why we use it. It's the best electron acceptor that's routinely observed in nature. And then other molecules are better at donating electrons, and for our purposes, glucose is the biggest one that typically donates all the electrons in our cells. Lipids are also good for this purpose. And then hydrogen gas is one that's very common in the world. These molecules tend to be good at donating electrons, where oxygen is good at accepting them. Other molecules in the middle can carry electrons. So NADH and FADH and NADPH, if you've ever seen these molecules, their job is to carry electrons from one place to another. And so they have to be good at accepting electrons and good at donating electrons. And so one last thing, and students always have trouble with this, so make sure you pay some attention to it. Redox reactions do move electrons around. There are electron donors and acceptors, but also they are chemical reactions. So molecules involved in redox reactions are transformed. So A doesn't just gain the electrons, it also becomes C. B doesn't just donate the electrons, it also becomes D. And so this might or may not be easier for you when you see actual examples. But if you look at a diagram of the electron transport chain in humans, oxygen accepts the electrons and it becomes water. So it's actually combining with free protons to become water. And it must accept electrons for that to happen. And if hydrogen donates electrons, it must well, it donates electrons, it must become a proton. That's a hydrogen nucleus, just one proton, which is often abbreviated H+. So if hydrogen donates electrons, it has to become H+, or maybe part of another molecule. So you're always going to see waste products of redox reactions. So water is our big waste product of using oxygen, whereas glucose, our waste product, is carbon dioxide. So this is the real-world example that you've probably seen when you learned the respiratory system. You learned that this is the reaction that makes it necessary to have a respiratory system. Because we need to get oxygen into our cells. We need to get carbon dioxide out of our cells. Well, carbon dioxide is the waste product you get when glucose donates electrons to oxygen. So glucose is made of 6 carbons, and they each become a carbon dioxide. Oxygen becomes water when it combines with protons. So, yeah, oxygen would act like A, it would gain the electrons or accept them, and glucose would be B, it would donate the electrons. So work through this slide, make sure you can interpret all of this, and next we'll look at ATP.